Here we present our VLDB Journal work titled Incremental Preference Adjustment, a Graph Theoretical Approach. Learning users' preference is critical to personalized search and recommendation. Let's start with a real house seeking scenario in Melbourne to describe the background, motivation, and goals of our work. A typical real estate search engine usually contains 1. A database storing all the houses, and 2. Vector embeddings of the user and houses as the outcome of any current preference learning model. Then, for user Amanda with a preference vector W and a house, the extent of Amanda being found of H is computed as the dot product between W and H, and the ranked list of house can be found in this way. Well, such a preference learning is usually one-shot offline process, while users' preference may change over time. Then how can we keep the model up to date with respect to user interaction in real time? Also, it remains an open challenge for CoStar case. Among the feedback that Amanda can provide to the system, a very natural question is to ask why house 3 is not ranked higher than house 2. Because it's always easy to tell which one she likes more between two houses, but it may be difficult to tell how to weight each dimension of a house she prefers, right? The above question can be formulated as a rank reversal operation on two items x and y, and we want to adjust the delta W such that the rank of x and y is reversed. From all of such rank reversal requests, more and more about Amanda's personal preference is revealed, and hence Amanda's preference vector can be incrementally adjusted to meet her preference. Specifically, our objectives on preference adjustment are twofold. First, we want to restrict the adjustment delta W to be decomposable into a valid flow on specific constraint network. Second, we want to minimize the number of non-zero dimensions in delta W, and we call this rank reversal problem the minimum dimension adjustment. Our work exhibits two sweet features. First, our work is orthogonal to the choice of preference learning models. Second, despite how good or bad a previous vector learned by existing model, we can always incrementally adjust the preference vector to a better place for every user. They exactly help address the two pain points mentioned last slide. Our theoretical findings are threefold. We prove that the MDA rank reversal problem is NP-hard. We propose a 2.17 approximate algorithm, provide that an optimal solution for another NP-hard problem is given. We further design two heuristic algorithms, first iterative linear programming and second iterative successive shortest paths that exhibit different degrees efficiency effectiveness trade-off. We also conduct an interesting study on measuring the adjustment effectiveness. We use the preference vector learned by existing learning models as the ground truth of the user. In particular, three classical models are used: PPR, WARP, and APR. Then we start from a randomly initialized W and compare the recall on top 100 items. The figure here shows the result of our methods on the Amazon dataset. It's exciting to see with 30 rank reversals, we can quickly achieve 50% recall, and it goes to 70% with only 60 rank reversals. Thank you. We hope it motivates you to read our paper.